Now to call up our next speaker, Professor Tony White from the Queensland Institute of Medical Research, who's going to talk to us about integrating computational and in vitro approaches to achieve drug repositioning for PWS. Welcome.
Okay, and thank you very much for the opportunity to speak here. I feel like a little bit of an imposter because this is something that we're just getting into now. We haven't been working on this for years like so many of you, but my research group has a lot of experience in neurological diseases, and as mentioned earlier by Tony, that's a major part of PWS, and hopefully we can bring our skills into this area combined with some of the other people that we collaborate with. And so the way we're approaching this is drug repurposing. And obviously, there aren't a lot of treatments available for PWS. And drug repurposing really gives you an opportunity to bypass a lot of the very long, slow and costly processes involved, where it can take decades and hundreds of millions, even billions of dollars to get a drug into the clinic. That's very hard to get funding for diseases like PWS. And so drug repurposing allows you to take drugs that are already out there in the clinic being used to treat other diseases and then repurpose them or reposition them to treat disease like PWS and other diseases and so on. And this has been quite successful in other areas. So it's not like this is a new concept. It's working very well across a lot of different areas where you can take a drug that's already out there and it's been repurposed. So there are examples already out there that will show you that it can work. And so our focus is more around the neurological changes, and again, as mentioned by Tony, that these can drive a lot of the other changes that you see in the disease. If you can target them, then you may be able to fix a lot of other things that are happening in the disease. But of course, there's no real treatments to target this at the moment. So we've been working with Zach Gehring, who was originally at our institute. He's moved to WEHI in Melbourne, but we still work closely with him. And he has a computational system, which I don't understand the computer component behind it, but he's done a lot of work around this where they're able to look at the genes involved, for example, in this case, PWS, and don't worry about the names of the genes. It doesn't really matter here. So there's all these sort of genes that are involved in the disease. He's able to take all those genes and look at how they're combined with other genes. So no gene is ever expressed by itself in a cell or in a body. It's always a part of large groups of genes that do lots of complex things together. So you can look at the way that all those other genes interact with this particular PWS gene. And then there's also a lot of data out there already about how drugs that are in the clinic will target particular genes. And that might be a gene that's interacting with a PWS gene. And you can say, well, from the data, it suggests that if in PWS it interacts with this gene and this gene goes down, we want to go back up, and this drug will actually increase that gene level. So that's the kind of approach. And so he's got a really great pipeline for doing that. And we published something on this a couple of years ago. And we've actually done this on several diseases now and been quite successful. So originally we started with some funding we got from Batten Disease Australia, which is a childhood dementia disease. And we used Zach's algorithms to identify about 80 drugs that are already out there in a clinic that could potentially target Batten disease and other childhood dementias, lysosomal storage disorders. There's many of them. And recently, Zach has also done another analysis that we've got some funding from motor neuron disease research foundations, where he's identified some drugs, a number of these originally known to target cancer, and they may be important for targeting motor neuron disease. So again, it's kind of repurposing drugs to treat brain diseases. And what we actually started off in this area was when Zach identified drugs that could target Alzheimer's disease. And the third drug highlighted on the list is memantine. And that's a drug that's already out there in the clinic being used for Alzheimer's. So his approach actually identified one of the drugs that are already out there. And usually his analysis actually identifies any drug that's already out there. It comes up. So it shows you that you're able to identify things that do work, but also other drugs that therefore may work. And so we tried some of the other drugs that he identified. And on the graph over on the right, on the far right is the red dot, where that's when we treat cells with something that induces inflammation. On the far left is healthy cells. And with some of the drugs you see with the purple circle, bring it back closer to the normal state. And so we're actually able to show that there are potential benefits there. And so what we've done is test some of these drugs that Zach has come up with in various systems. So again, we're talking Batten's disease, which is a childhood brain disorder. And we've taken cells from people with that disease, grown them into different types of neuronal cells, and then treated them with the drugs. One of the things that comes up in these cells is what we call cathepsins. So these are enzymes in the cell that break down waste that accumulates in the cells. And in the disease, these enzymes have lower levels, as you can see there with the red arrow, compared to healthy cells. And therefore, you get this accumulation of waste, which tends to kill brain cells. And we found that treating with some of the compounds that Zach identified that are already out there for treating things like cancer and even COVID, they were able to increase the expression of these very important enzymes. So the first drugs we tested from his analysis actually had quite a positive effect. And something else we look at is inflammation. And astrocytes are cells in the brain that are involved in inflammatory processes, and they are upregulated in Batten disease. And when we treated them with the same drug we saw in the previous slide, it also inhibited the inflammation in those cells. So again, another positive outcome from one of the first drugs we tested. And so what we're doing now is Zach is going to very shortly identify the compounds that he thinks are at the top of the list for treating PWS, probably particularly around brain processes. But the data he generates will tell us what the best cell types are, because all the genes that are changed, he's able to map them to the particular types of tissues and cell types. So we assume that there will be brain pathways involved, but if there's not, then we can grow them from our stem cells. We can grow any cell type, and we just need to work out what is the best way of measuring the changes in those cells. So he'll come up with a list of drugs, and we'll put them on the cells that we generate and see how we go. Let's say, given the fact that we've got lots of positive data from his work previously, we expect to have very good outcomes. So just to summarise, there's currently no sort of effective treatments, particularly for the brain effects of the disease, and drug repurposing is really an exciting area because it can cut the time to treatment down many, many years, and a lot of funding that's required. And we've done this with other diseases, so we know that the system works, and we're going to apply this to PWS. And then once we've got the analysis and we'll screen these drugs, and then we'll take it from there, probably screening in larger numbers of cells, and then we can look at potentially going into clinical trials and so on. And so just really like to thank the Prader-Willi Research Foundation for giving us this opportunity to get into this area. And I'd just like to say that about 6 years ago, so we got funding from motor neuron disease research foundations in Australia to get some of our systems up and running. And now we've had about $3 million grants from various groups, Australia, internationally, and industry, to keep working in those areas. And that was really something that was built on just a small amount of money to start with. So it's really something that we can grow from just a small input to just get us going in this area, and something that we'll be very passionate to follow. Thank you.
Really limited amount of time today, so if you have questions for any of our speakers, please seek them out. But as we've stated, we've got quite a bit to move through. we need new drugs and we need to get more out of existing drugs. There's a lot of value in repurposing, and that looks like an incredibly interesting project. It may be connected in some ways to the skill set of our next speaker.